好，各位专家晚上好，非常荣幸啊，今天晚上利用晚上的时间和邀请到两位英国的钢结构协会的英国的不锈钢钢结构协会的两位专家，为我们呢讲解一下呃不锈钢结构的相关的设计工作啊，相关设计工作。首先呢，第一位报告人呢是 Nancy 教授，下面呢我简要的介绍一下这个 Nancy 教授的这个简历啊。Nancy 教授呢是英国钢结构协会的副主任，英国土木工程师学会会士。在过去的35年时间里呢，他一直致力于不锈钢结构性能的研究，并为全球的各个国家撰写推广设计标准和指南。他是欧洲不锈钢规范 EN 1993-1-4的技术委员会主席，并审定了最近的欧洲规范的3个版本。此外呢，他还参与起草了美国的不锈钢结构设计规范 ANSI AISC 370，还有 ASC 8-02，以及美国的这个设计指南27。目前呢，他致力于制定不锈钢在桥梁以及在核电结构中的一些设计指南也是报告的过程中呢，各位专家可以通过这个聊天框因为我这个把大家的这个声音静音掉了，但是可以通过聊天框，随时呢向我提问，然后在这个大约有最后呢留下5分钟的时间，然后我请那个 Nancy 教授呢把大家提的问题里面的代表性的问题呢，给大家解答一下，好吧？这就是一个非常简单的简介。为了便于大家听报告的时候，因为报告专家是英文的，用英文来讲，所以呢，我做了一个非常简单的就是随时的翻译的这个情况。目前呢，我共享一下我的屏幕啊，大家应该能看到我的屏幕，能看到我的这个屏幕的这个状态。也就是第一步呢，你要点一下这个下面应用这个位置。应用这个位置呢，有一个里面有一个开启字幕。你点它一下，它就可以了。点它一下以后呢，再把这个旁边的小箭头上点击声音来源，选择自动识别中英文。然后呢，第二列呢，这个翻译语言呢，翻译成中文。打个勾它有个勾的时候就是对的，这边也应该有个勾，所以有5步。第一步点应用，第二步点开启字幕，第三步呢把这小箭头往上点一点，然后呢再选择声音来源，然后再选择翻译成的这个结果翻译结果。大概就这5步希望大家能够做好设置，然后享受我们这个 Nancy 教授带来的这个报告我把我这个共享关掉。好so next we welcome the Professor Nancy to give us a presentation about the European Code. Hello, Nancy.
Hello.
Hear me?
Hello,
Yeah.
everyone.
Yeah.
Can you hear me?
Yes, I can hear you very clear.
And can you see my screen?
Yes, very clear. Yeah.
Okay, well, let's make a start. Good afternoon, everyone, and welcome to our first presentation, which gives an introduction on the use of using stainless steel in construction. Our focus is on load-bearing stainless steel, so not so much on cladding or roofing, more on load-bearing members. At the Steel Construction Institute in the UK, we carry out a range of activities such as writing standards and technical publications. And we have been closely involved in writing standards for Europe and the United States on structural stainless steel for many years. This is our webinar series, 2 talks today and 2 next Tuesday. After each talk, there will be 5 minutes allowed for questions. And if you like, you can put your questions into the chat box. My presentation today is divided into 5 parts as follows. Firstly, an introduction, then I will show you examples around the world of load-bearing stainless steel, and then we get into details, properties, specification, and how to choose the right stainless steel for your project. So let's start with explaining a few things about stainless steel. What is it? It is the name given to a family of corrosion and heat-resisting alloys of steel, in which you have chromium, the element chromium, at least 10.5% by composition, and you have less than 1.2% of the element carbon. When you have this composition, a transparent and tightly adherent layer of chromium-rich oxide forms spontaneously on the surface of the steel, and that is what protects it from corrosion. If this layer gets scratched or damaged, it will reform spontaneously, providing oxygen is present. There are lots of different stainless steels, each with slightly different strengths, corrosion resistance, and other properties. But the good news is that only a few are used in construction in structural applications. And those are the ones we're going to introduce to you today. Stainless steels are grouped into families, which have different microstructures and mechanical, physical properties. So each family has different alloying element combinations, and the elements chromium, molybdenum, and nitrogen, they are the most important alloying additions for improving corrosion resistance. The element nickel is primarily helpful for improving the formability and weldability. So let me quickly introduce you to the 5 families. Austenitic stainless steels, they're ductile, reasonably strong, readily formed and welded, and their strength increases with cold forming. Duplex stainless steels, they have a mixed microstructure, austenitic and ferritic. It is not a coating system. It is the microstructure that is mixed. Duplex stainless steels are stronger than austenitics, but this also means they're not as easily formed and require greater care when being welded. Ferritic stainless steels are the 3rd family here. They're less strong and ductile than the austenitics, and their corrosion resistance is also generally inferior to the austenitics. They tend to be used in thin gauge applications, and there are many examples in China of ferritic stainless steel being used for cladding applications. Let's move on to precipitation hardening stainless steels. They have very high strengths, similar corrosion resistance to the austenitics, and they are used mainly for high strength bolting applications in the aeronautical industry. And then finally, the martensitic stainless steels. They are less corrosion resistant than the austenitics, and you will find them in your kitchen. They are the stainless steels we use for kitchen knives. The stainless steels used in construction are from the austenitic and duplex family. And within both families, there is a wide range of corrosion resistance, which depends, of course, on the alloying content. Now, most applications by a long way are austenitic stainless steels in construction. However, for weight-sensitive structures, such as bridges and offshore platforms, then duplex stainless steels will often be a better choice. And I put on this slide a note that the higher the alloy content, the more corrosion resistant the alloy, and the higher the cost. Let's turn now to consider when you might use stainless steel in structures. Clearly, it's more expensive than carbon steel, and so there are only some particular applications where it makes good sense to use stainless steel. And stainless steel can be used in visible applications or in applications which are hidden from eye. They may be large members or they may be very small components. They can be architectural showstoppers or they can be very basic utilitarian applications. Firstly, and most commonly, you would use stainless steel if you had a structure needing excellent corrosion resistance and you wanted to avoid the need for a coating. So when might this be? For structures, say, in the food and drink industry or the chemicals industry, there may be a very strong reason why you don't want to risk a painted coating peeling off and contaminating the process that's taking place within the structure. Stainless steel makes sense for those types of structures that have very long design lives. So I'm talking about structures such as bridges and nuclear structures where the design life might be over 60 years and maintenance is just hugely expensive and something you want to avoid. Then, of course, the higher construction cost is outweighed by the lower maintenance cost. Another reason for stainless steel is if you want a particular exposed metallic finish for a sculpture, some sort of landmark structure, or if cleanability is very important, say in the water, food and drink industry. Something you may not know is that stainless steel is highly resilient, and this is the reason why it's used in blast resistant structures, say on offshore platforms, or structures that need to have good crash resistance, and has led to applications also in lock gates and other barriers. The austenitic family of stainless steels are very tough at low temperatures, and this leads to applications, say for Arctic structures. I know there are applications in China where the excellent properties have been used. Also, the chemicals industry and other applications which require very good toughness at low temperatures. And finally, perhaps surprisingly, austenitic stainless steels are non-magnetic. So you need these properties in some medical or defense applications. So again, stainless steel is a good choice there. Now, let's move on to the second part of the presentation, where I'm just going to take you round the world and show you a few examples of load-bearing applications. So let's start with some buildings and external structures. So here I'm showing a viewing platform. Quite obvious, isn't it, why stainless was chosen for the viewing platform, because it's right by the sea. And then if we move down, a local structure are the stainless steel tree-shaped columns in Nanjing. And there are 42 of these beautiful structures, 42 stainless steel trees supporting the roof. Now, I think stainless steel was chosen not only because of the appearance, but also the corrosion resistance in a warm and moist environment. And then the photo I show on the right is in Beijing, and this is a different type of structure altogether. It's a large glass cable net wall, 90 meters high, 60 meters wide, and it's using duplex stainless steel connections for the cable and tension rods, and the tension rods also are duplex stainless steel. Subway entrances has proved to be quite a popular application of structural stainless steel. There are at least 40 canopies now in the US, Washington, DC Metro. Why stainless steel? Well, it looks good, it's corrosion resistant, it's resilient. These canopies in the Washington, DC Metro, it was a modular design because speed of installation was hugely important. So the modules were bolted together on site, made up of rectangular hollow sections. And the subway entrance I'm showing on the right is using duplex stainless steel because very high strength was needed for this subway station that was flooded and a huge amount of damage caused during Hurricane Sandy. I've already mentioned that stainless steel is used for cladding. I've just shown one example here in the Middle East where an austenitic stainless steel was chosen for cladding, and in China there are quite a few applications of ferritic and different grades of austenitic stainless steel used to create different effects in the cladding of high-rise buildings and other structures. Of course, sculpture is a popular application of stainless steel. I love the Cloud Gate structure in Chicago. And would you believe it's made up of 168 stainless steel plates welded together. It's highly polished, you can't see the seams, and it weighs about 100 tons. Now, moving on from cladding and structure, this I feel is the most important area where structural stainless steel is used. Often because these are corrosive environments and you do not want to have to go back and do maintenance and reapply coatings. So this application here is a pharmaceutical plant, and you need stainless steel platforms to access the vessels, lots of instrumentation needing access. And so these are hollow sections welded together of structural stainless steel. The other photos I'm showing on this slide are for offshore platforms in the water and wastewater industry, the pulp and paper industry, lock gates, and also in the nuclear industry. So the drivers for using stainless steel are clear: corrosion resistance, long life, minimal maintenance, no risk of contamination from paint peeling off. And then finally, I wanted to tell you that there's growing interest in the use of stainless steel for the structural members of bridges. I guess you've come across stainless steel for the hand railing, but I'm actually talking about the structural members of bridges. And this is where duplex stainless steel is particularly useful because of its high strength. These are weight-sensitive structures, and often the installation process is very sensitive to the weight of the structure. Cutting weight opens up different ways of installing bridges. So I've shown here the Stonecutters Bridge, which is it 25 years old perhaps now, where stainless steel is used to act compositely with concrete in the upper parts of the columns. We've also, there are a number of pedestrian bridges made of stainless steel. There are road bridges, and there are bridges carrying railways. So all again, the reduction in maintenance, particularly over water or running over a railway, is very beneficial for using stainless steel. Right, let's move on now to the properties of the structural stainless steels we're talking about. Looking at the graph, the green lines show the stress strain characteristics for austenitic stainless steel, and the blue is for duplex. I've shown in red typical carbon steel stress strain curve, and in black what one might expect for an aluminium alloy. It's clear that stainless steel has different stress strain characteristics compared to carbon steel. You see this phenomenon we call strain hardening. Sometimes it's called cold working. It basically means increased strength by plastic deformation. And it can be very useful in design. We'll talk more about that a little later today. Of course, there can be disadvantages too. Stainless steel, because it strain hardens, It can require more power when it comes to forming or cutting. Looking back at these stress strain characteristics, you will see there is gradual yielding, or if you like, a gradual loss in stiffness. And it is this that leads to differences in the resistance of members to buckling instability. And that is why different design code is needed for structural stainless steel. What do we use for the yield strength? We use a parameter called the strength at the 0.2% proof strain. And that is the same as used for any metal that has similar stress strain characteristics. And it's this parameter that is given in your material specifications. Now, let's look at what happens at the full range stress strain curves. Again, austenitic in green, and immediately you see austenitic stainless steels have very high ductility. You can't always benefit from this high ductility, but in some applications you can. And I've showed those on the right-hand side of the screen. Stainless steel has excellent energy absorption properties, much better than carbon steel or aluminium, due to its high rate of strain hardening and excellent ductility. Duplex stainless steel has similar ductility to carbon steel. Just to summarize things, I have a table here showing the mechanical properties and the strength used in design, the yield strength. You can see the austenitics have a yield strength around 200 megapascals, and the duplexes is more than twice, around 450 megapascals. Because of the strain hardening, the tensile strength is somewhat higher than you might expect, around 500 megapascals for austenitics and 600 for duplexes. So you get a sense for the effect of strain hardening when you look at the ratio of the tensile to yield strength. Note too that the modulus of elasticity that you need in your buckling calcs is very similar to carbon steel. So this is the initial modulus of elasticity. And these properties are in the annealed condition. Now, this is a word you may not have come across. It basically means in the softened condition before any strain hardening has taken place. Some surprises here when we look at the physical properties due to the different composition of stainless steels. First, the thermal expansion for austenitic stainless steels here is about 30% higher than that for carbon steels. So where you use carbon steel and austenitic stainless steel together, which is quite common really, you need to take account of the effects of this differential thermal expansion. Moving to thermal conductivity, you see a big difference between stainless steel and carbon steel. So the thermal conductivity of the stainless steels is only about 30% of that for carbon steel. So this is good, and it can also be bad. It's good because materials with low thermal conductivity prevent the transfer of heat. So this can help in achieving enhanced energy efficiency, and stainless steels are sometimes used in thermal block type components for this reason. When it's bad is when you're welding and you want the heat to dissipate, and it doesn't dissipate so quickly because of the low thermal conductivity. So there are special procedures that give guidance on welding to minimize distortion, which might occur because of the lower thermal conductivity. I've already mentioned this, that austenitic stainless steels have excellent low temperature toughness properties. They in fact show no ductile to brittle transition down to really low temperatures, cryogenic temperatures, shown by the grey bar. Duplex stainless steels, well, they are a bit more like carbon steels, so they do show a ductile to brittle transition. And they are shown in the yellow bar, the standard duplexes more to the left and the leaner duplexes more to the right. But generally they show good toughness, enough needed for structural applications down to minus 40 degrees C, and perhaps even lower. So that completes what I was going to talk about properties. We're going to hear much more about designing structural stainless steel after the break. But I'm now going to explain how you specify stainless steel for a project. When we talk about a stainless steel grade or type, we actually mean an alloy, i.e. a chemical composition, and not a strength. I mean, when we talk about carbon steel, we generally are referring to the strength of the carbon steel. But for stainless steel, it is the alloy and composition. So for the families of stainless steels used in construction, most of the austenitic stainless steels have the same yield strength, around 200 megapascals. I say most because there have been some interesting developments in China, and some high nitrogen and low nickel austenitic stainless steel alloys have been recently developed with higher strengths. So I'm just saying that the most widely available austenitic stainless steels will have a yield strength of around 200 megapascals. And the duplexes, no matter what their composition is, they will almost all have a yield strength of around 450 megapascals. I will briefly introduce the Chinese standards that are available for and relevant for load-bearing stainless steel members. And firstly, the standard that gives the alloys and the chemical composition and physical properties, that is GBT 20878. That standard contains lots and lots and lots of stainless steel alloys which are appropriate for use in a wide range of industries. Then GBT 4237 is the standard that covers the hot rolled stainless steel plate and strip. So these are the thicker product forms, with the thinner products covered in GBT 3280, which covers the cold rolled stainless steel plate and strip. So the cold rolled would be the thinner gauge. This is the time when we're going to open up the Chinese stainless steel structural technical specification, CECS 410, and see what it says about stainless steel alloys. Now, the third talk in our webinar series is devoted to this standard, so I'm just going to say a very little about it. The CECS 410 says clearly that for load-bearing structures, austenitic and duplex stainless steels in table 331 may be used. And I'm showing this table on my slide. And the Chinese designation number I'm showing in red. So you can see the S for steel and then the 5 digits. So first, there are the standard or basic austenitic alloys, 2 of them. Then there are the austenitic alloys that contain molybdenum, so they have better corrosion resistance, and there are 2 of them. And then there are the standard duplexes. There are 2 there. And there is 1 lean duplex. Now, what do I mean by lean duplex? I mean the alloying composition is it's less highly alloyed. So it has slightly less corrosion resistance compared to the standard duplex, but still very good corrosion resistance. It means it is a cheaper alloy, but it's not appropriate for use in the most corrosive environments. Now, what about ferritic stainless steels? There are 6 ferritic stainless steels listed in the Chinese standard, but it clearly says that they are not for load-bearing applications. Perhaps you remember that I said generally ferritics are used for lighter gauge applications such as roofing and cladding. So the strength of the austenitics is around 200 megapascals and the duplexes is around 450 megapascals. I'm not showing the newly developed austenitic, which I mentioned, which has a higher strength. We're just focusing on the more widely available ones at the moment. I hear you asking, what is the difference between S30408 and S30403? And the difference is that S30403 is a low carbon alloy. Now, low carbon alloys should be specified if you're going to do welding, because the low carbon reduces a risk of a particular form of corrosion called sensitization and intergranular corrosion in the heat affected zones of welds. So that is why you should specify the L grades if you need to weld. These days, you often find the stainless steels dual certified. So you may find that when you purchase the stainless steel, it meets the criteria for both 30408 and 30403. And exactly the same for the 316s. There is a standard carbon and a low carbon. Now, let's look at the Chinese product standards for hollow stainless steel members. So this is a hugely popular product form, widely used in load-bearing applications. So I could find 3 Chinese standards. GBT 14975, this covers the seamless stainless steel tubes. And then there are 2 for welded stainless steel tubes. GBT 12770 is really geared more towards mechanical structures, automotive parts, bicycles, furniture, general engineering, whereas JGT 539 is geared more towards construction, so probably that's the standard you would want to specify. So for architectural, handrails, structural components, and this standard places a greater emphasis on the surface finish, corrosion resistance, structural integrity. Briefly then, what are the standards covering the lighter gauge stainless steels? Well, I've got 2 here I'm showing you. GBT 34200 covers the flat light gauge sheet coil stainless steel products, and then 36145 covers the corrugated and profiled sheets. And you see, I wrote at the bottom of the slide that the Chinese technical specification says that austenitic, duplex and ferritic stainless steels are permitted for cladding and roofing. I've never come across duplex being used for cladding and roofing, but certainly ferritic and austenitic are widely used. Let's move now to stainless steel fasteners. And here, the family of standards are GBT 3098, and part 6 covers bolts, screws and studs, and part 15 covers nuts. Before I explain how to use the standard, I would just like to emphasize that fastener assemblies should have equivalent corrosion resistant to the most corrosion resistant alloy being used. Very often you see that this guidance has not been followed and you see horrible corrosion. So it's important that you specify the bolt and the nut so that it is at least equivalent to the most corrosion resistant alloy being joined. So a few slides introducing you to the Chinese standard for stainless steel fasteners. How you name a fastener is first by the letter A for austenitic, D for duplex, followed by a number 1, 2, 3, 4, 5, or 8, and that tells you the corrosion resistance. 1 is the least durable and 4 and 5 are the most durable. You really shouldn't use steel grade A1. That doesn't have very good corrosion resistance. So the most common bolting alloys you'd be using are grade A2, which is like a 304, and grade A4, which is like a 316 in terms of corrosion resistance. And then the final 2 numbers, they tell you the strength. And it's called property class, but you can see here there are property classes 50, 70, 80, and 100. So I will tell you a bit more about the strengths in another slide, but I wanted to first of all show you the duplex naming system. So here we have, starts with a D, and then the 2, 4, 6, or 8 tells you how corrosion resistant it is. So a D6 is your standard duplex. D2 and D4 is the lean duplex. And then we have the strength. Duplex stainless steel fasteners are not as widely available as austenitic fasteners, but if you're joining duplex stainless steel, it really is recommended that you use duplex fasteners. So finally, on fasteners, here is a table showing you the tensile strength. So let's look at, for example, A470. That's a really common stainless steel fastener. And you can see that its tensile strength is 700 megapascals. If, however, you needed a higher strength, then you would consider specifying A480, which has a tensile strength of 800. What about surface finish? Many surface finishes are available with stainless steel. Firstly, let's talk about the mill finishes. So these are the finish straight from the production mill, most common, and it's a standard finish for heavier sections. It's dull, it's non-reflective. You think, is this stainless steel? But it is. Stainless steel doesn't have to be shiny. So in the European standard EN 10088, the number 1 is used to determine a hot rolled finish, and number 2 for a cold rolled finished. And for architectural applications, cold rolled surfaces would generally be chosen. They're smoother and to tighter dimensional tolerances. But of course, we don't stop at mill finishes. There are many special finishes also available for stainless steel, generally applied at polishing houses further down the supply chain. And these may be ground, brushed, polished, even patterned and coloured. The smoother the finish, the better the corrosion resistance and the better the cleanability. Why? A rough finish is more likely to retain contaminants than a smooth finish, and rain washing is less effective on a rough finish than a smooth one. And a rough finish has more micro crevices than a smooth one. But of course, a smooth finish is a more expensive finish. So you really have to weigh up the advantage of a smooth finish against the additional cost. Now, the final part of my talk is to lead you through the process of alloy selection. How do I choose the right stainless steel alloy for my project? The most important part of your choice is the service environment. By that I mean, where is the structure that you're designing? And it is important that you characterize the environment carefully. And most of my talk is assuming that the structure is in a atmospheric environment. So the issues you're concerned with are chloride salts. Is the structure close to the coast, or do you use de-icing salts in cold weather? What type of de-icing salts do you use? Is the structure in a polluted industrial environment? Is there a lot of pollutant in the air due to traffic? Is the structure going to be washed by rain or sheltered. Washing by rain is good. Stainless steel loves water. So washing by rain is good. Sheltering is not so good, because then you can have an accumulation of chloride salts or other contaminants. And another thing to consider is the structure going to be cleaned? Or is it going to be left with no maintenance regime? So you can see on this slide, there are other considerations. How do I choose the right stainless steel alloy? Can I use the additional strength of duplex? Do I need very good low temperature toughness? Think about austenitic. Think about the details of your design. Are there going to be lots of crevices? Do I need really very good corrosion resistance because there is a risk of crevice corrosion? Think about the fabrication. Is there a lot of welding? Will it be difficult to avoid the distortion that happens with welding austenitic stainless steel sometimes? Think about the surface finish. Sometimes it's easier getting certain surface finishes on austenitic stainless steels rather than duplex. I've mentioned maintenance. What about product availability? Will the alloy I've chosen be available in the product I need? And of course, cost comes into everything. So in my closing slides, I've just tried to summarize some key points on alloy selection. Left-hand side, standard chromium nickel austenitics. Right-hand side, the molybdenum austenitics. So the standard austenitics, most common by a long shot in construction, suitable for rural, light urban environments, whereas the molybdenum austenitics can be used in more corrosive environments. They both come in low carbon variants, both suitable for low temperatures, and both available wide range of product forms. What do you need? Rod, fasteners, hollow sections, plate, cold form channels, angles. They're likely to be available in austenitic stainless steels. Duplex stainless steels. So here we have the lean duplexes on the left and the standard on the right. The lean duplexes have a corrosion resistance similar to the 304 and 316 austenitics, whereas the standard duplexes are suitable for severe corrosive environments. Now, the duplexes are not as widely available, but hollow sections can still be procured, bolts also available, and remember, twice as strong as the austenitics. Our time is short, and I would refer you to expert guidance on alloy selection given in these 4 resources. Firstly, your own Chinese technical specification contains guidance on alloy selection. There is guidance in the European Design Manual, which you can download based on the Eurocode. However, when it comes to alloy selection, the system has been calibrated for European environments. So you shouldn't adopt that without making some modifications. There is guidance in the American stainless steel standards, which I think you would find helpful. Free download, AISC 370. And there is also this excellent tool hosted by the IMOA website It's called the Site and Design Evaluation System, particularly good for architectural applications. Finally, I have to tell you that caution needs to be exercised when stainless steel members containing high residual stresses, say due to cold working, are used in chloride-rich environments, particularly indoor swimming pools, and particularly at the ceiling level where contaminants tend to accumulate. And you need to watch out for components such as highly loaded cables, as they may be susceptible to stress corrosion cracking. So the general advice that if you have a load-bearing member in an environment like this that cannot be cleaned very regularly, then you should not use the standard austenitics. You need to use a more highly alloyed stainless steel, perhaps a 6% molybdenum super austenitic or a super duplex, and very regular inspection should be carried out if the wrong stainless steel has been used. This completes what I'm going to talk about this morning. I've summarized what I've said there, different grades for different environments. Now, if anything I've said has been interesting and helpful to you and you would like to go back and check it out, a recording of all the talks we're giving and the slides as PDF will be hosted on this WeChat channel and the IMOA Chinese website after the webinars. And we have a few minutes now. If there are any questions, I'm happy to take them.
各位专家，这个非常感谢啊，我们 Nancy 教授给我们一个非常应该说从非常大的一个方面介绍了不锈钢结构的一些选材啊、力学性能这方面的东西。看看各位专家有没有一些问题啊？你可以这个，因为现在我们涉及了禁言的你可以举手，就是在这个窗口下面有一个举手的这个标记，你点一下举手，我能看到你举手的时候，我可以把你的话筒给你打开。我看看聊天里有没有一些消息啊，稍等一下，看各位专家的有没有什么问题啊？So there's a question from the message. Could you hear me, Professor Nancy?
Yes, I can hear you. Yes, carry on.
Yeah, that's the question. So I can paste that to. Maybe you can see. Could you see the message?
Ah, yes, I can see it in the chat.
Yeah, that's about welding, maybe corrosion resistance between the carbon and the
yes.
stainless steel.
How should we handle the restrained thermal stresses induced by temperature variations in design? This is an excellent question, and it is very commonly encountered connecting stainless steel to carbon steel. You very rarely have a structure that's completely stainless steel. So there is a lot of experience in how to do this, whether you're bolting or welding. We will mention this in the next talk, but you're quite right that care is needed to restrain the thermal stresses due to the differences in thermal properties. And there are specific recommendations in the Eurocode and in the American code. For example, let me just mention welding. If you're welding stainless to carbon steel, your carbon steel clearly has a painted coating on it, unless it's weathering steel. So the paint coating should be extended over the weld and onto the stainless steel for, I forget how much, for 50 millimeters, something like that. And this is to avoid the possibility of any bimetallic corrosion. Of course, I should have said, you'll only get corrosion if you've got moisture. But this is good practice to extend the painted coating that you've got on the carbon steel onto the stainless steel for about 50 millimeters. And if you're welding stainless to weathering steel, then you would have to paint a strip over the weld and onto the stainless steel, again, to avoid bimetallic corrosion.
So I translate it in the Chinese, so make sure everybody understand it. Yeah.
Oh yes, okay.
我刚才因为这个问题是问的非常好的，也是我们规范编制过程中的一个非常，应该说非常重要的问题，就是不锈钢和碳钢焊接起来，无论是它的热应力啊，还是它的这个后来的防腐怎么做。刚才呢，Nancy 教授说，在这个下一次报告里面，下一次的报告里面会专门提到，会这个就是不锈钢和碳钢的焊接的问题。现在目前呢。欧洲规范和美国规范里面都应该有一点规定啊。目前中国规范里面新版的也会有一点的规定，就是要做防腐涂装，越过刚才说是越过这个焊缝，然后50毫米，或者说可能更大的一点的区别，也就是说这个不锈钢这一块区域也要做一点点涂装，来降低它的这个电位差的这个点啊。希望大家能够理解。看还有什么其他的问题吗？如果有其他问题，您可以在这个就各位专家都可以在这个群里举手啊，举手，我就能看得到，我可以把话筒开开。另外呢，在听下一个的报告过程中，你有什么这个想问的问题，哪怕超越了这个报告的范围，你也可以在这个就是因为现在可以单独和我这个聊天，就在这个群里发消息，我是能看得到的。那我能看到，我会把这个问题总结下来。给各位专家最后再做一个回复。好，so now let's move to the second half. Yeah. So let me first introduce Dr. Francisco. So before this, 在这之前呢，我想还是要给大家说一下这个怎么来用这个就是我们的这个英文的翻译这个过程啊，稍微1分钟的时间啊，1分钟的时间，大家应该能看到我的这个屏幕共享啊，屏幕共享呢，现在呢应该说，现在呢应该这个 AI 的手段是比较多的。现在我们呢推荐了大家怎么来做呢？就是在我们这个腾讯会议的过程中，你可以点击应用啊，这个应用呢点它一下以后呢，会出来一个选择框，在这个选择框里呢，你再点一下这个地方叫开启字幕，你点了一下就行了，点了一下它呢会显示关闭字幕这几个字，说明你已经开了。开了之后呢，这边有个小箭头，这个小箭头你点它一下呢，会出来很多的选择项。第一项呢叫声音来源，建议大家选择自动识别中英。这个时候呢，你选择好了以后呢，这会打个勾，会打个勾。然后呢，在这个就是翻译语言呢这边选简体中文，你也打个勾。所以做完这5步以后，您那边就是国外专家在讲的过程中。它大致我也试了一下，大致能够一个比较正确的翻译啊，比较正确翻译。希望大家能够就是如果这个在电脑旁边或者在手机旁边，你可以试一下这个操作啊，应该还是比较管用的啊。这个是我这边的一个简单的一个介绍啊，简单介绍。然后呢是我们就到第2个报告啊，第2个报告，第2个报告呢，这个报告人呢是也是这个英国钢结构协会的，叫Francisco 博士，他呢是谢菲尔德大学博士毕业，主要研究方向呢为冷弯这个型钢组合构建啊，参与了很多的科研项目以及新版的欧洲规范的撰写。 同时呢，它也参与了美国不锈钢结构设计规范 ANSI、ARIC 370，还有这个 ARIC 的指南这个 Design Guide 27，还有 Design Guide 41这个最后这个呢是专门关于紧固件的这么一个这个标准。刚才呢 Nancy 教授呢说这些标准从相应的网站上都是可以免费获取的啊，所以也这个后面我们这个PPT 啊和视频都会上传到微信平台啊，还有这个网站上。大家有感兴趣的可以到上面去下载下来相应的这个材料。目前呢，这个我们的Francisco 博士呢正在致力于制定双向钢的桥梁的设计的指南，以及不锈钢结构在抗震作用下的一些响应。行，Dr. Francisco, could you say hello to everyone?
Hello, everyone. Thank you, Baofeng. Can you hear me well?
Yes, well, I can hear very clearly.
I'm going to share my screen now, if it's possible.
Yes.
Could you please confirm? Yeah. That's great.
So, welcome.
Well, thank you, and hello to everyone. Good evening. My name is Francisco Mesa, and I'm going to be delivering this second part of this webinar, which is called Design of Structural Stainless Steel Principles and Eurocode Rules. So here you can see the outline of this webinar. I will start by explaining how the stress strain characteristic of stainless steel affects its buckling performance. Then I will give you a brief introduction about the Eurocodes, which are the design standards that are used in Europe. And then I will talk about how the Eurocodes address the design of stainless steel members, and I will tell you about specific rules that have been developed for stainless steel, which take into account, take advantage of the specific characteristic of stainless steel. And then to finish, I will talk about connections and the fatigue resistance of stainless steel. So just one second. Okay, so we will start by looking at the stress strain characteristic of stainless steel and carbon steel. And this figure shows typical stress strain curves for the main three stainless steel alloy families, and also a typical stress strain curve for a mild carbon steel grade. So duplex stainless steels are the strongest out of the three stainless steel alloy families, and austenitic stainless steels are the one that show the most significant nonlinearity and strain hardening. Now, by nonlinearity, what I mean is that the stress strain behavior deviates from the linear behavior that is characteristic for carbon steel. So that is before the yield strength is reached. So for carbon steel, the yield strength is well defined, and it corresponds to the point at which further increases in strain result in no increase in stress. So we are talking about this point here in the curve. And the region in which the stress does not increase with the strain is referred as the yield plateau. So that would be this region here. Now, for stainless steel, the yield point is not well defined, and the stress strain curve show this rounded shape without a sharp yield point. So because of this, the yield stress of stainless steel is obtained by offsetting the initial modulus of elasticity, which is represented by this red line, and is offset to a strain that is equal to 0.2%. Now, the point at which the red line now intersect the stress strain curve is what is considered to be the yield strength. Now, you can probably not see very clearly in this figure, but once you reach the yield strength of a stainless steel, if you continue straining the material, the stress will continue to increase gradually. So that means that there is no yield plateau. And this increase in stress beyond the yield stress is called strain hardening. And some of the design rules that have been developed for stainless steel structures try to take advantage of this strain hardening. So here I'm showing you the full stress strain curve for the 3 different stainless steel alloy families, as well as for carbon steel. And here you can see more clearly the strain hardening of stainless steel. So you can see how the strength increases gradually from the onset of yielding until the ultimate strength is reached. Now, for carbon steel, you can also see strain hardening after the yield strength is reached. But in order to develop this strain hardening, the material has to exceed the yield plateau, which is given by this portion of the curve. So from this figure, you can also see that stainless steels are as ductile as carbon steel or more. So the elongation at fracture of austenitic stainless steels is significantly larger than that of carbon steel. And for duplex and ferritic stainless steels, the elongation at fracture is very similar to that of carbon steel. So how does the nonlinearity of stainless steel affect its buckling performance? So if you look at any of the elastic buckling resistant formulas, you will see that they all have one thing in common, which is that they are all proportional to the elastic modulus of the material. So this is the case for local buckling, column buckling modes such as flexural buckling, or lateral torsional buckling in the case of beams. Now, the initial modulus of stainless steel is similar to that of carbon steel, but as you can see in this figure, it decreases gradually as you approach the yield stress. Now, because of the reduction in the elastic modulus when the stress increases, the elastic buckling resistance also reduces, which leads to a reduction in the resistance of the member. Now, you have to bear in mind that for carbon steel members, this reduction in the elastic buckling resistance does not occur until the yield strength is reached. And therefore, you could expect that the buckling performance of stainless steel is going to be slightly worse than that of carbon steel. Now, in most stainless steel design codes, the buckling resistance is calculated using the initial elastic modulus, and the reduction in the elastic modulus is accounted for by using different buckling coefficients in the resistance equations from those that are used for carbon steel. There are other factors that might affect the buckling behavior of a stainless steel and a carbon steel member, and these are the geometric imperfections and the residual stresses of the material. So the geometric imperfections are generally the same for carbon steel and stainless steel members, and they can be present at a cross-section level and at a member level. So imperfections at a cross-section level affect the local buckling resistance of the cross-section, and they include the out-of-plane imperfections of the flanges or of the web. And you can see that shown here in this figure. Imperfections at a member level include the out-of-straightness of the column, and for example, this would affect the flexural buckling resistance of a column, and that is represented here. Now, the residual stresses of stainless steel and carbon steel sections are generally different because of the different thermal properties of carbon steel and stainless steel, as Nancy showed you previously. The main thermal properties affecting the residual stresses are the thermal conductivity and the thermal expansion. So the thermal conductivity of stainless steel tend to be lower than for carbon steel, and the thermal expansion tend to be larger. And for austenitic stainless steel, the thermal conductivity is the lowest, and the thermal expansion is the largest. And they also show the most pronounced loss of stiffness, and because of that, they tend to exhibit the lowest buckling performance of all the stainless steel alloy families. Now, not all buckling modes are affected to the same degree by the nonlinearity of the stress strain characteristic or the geometric imperfections and residual stresses. For example, global buckling is known to be more affected by these factors than local buckling. And here I'm showing you what happened to a stainless steel column depending on how slender it is. So for columns with low slenderness, that means relatively short columns, the resistance of the column is governed by yielding, and therefore the beneficial effect of strength hardening will result in a stainless steel column reaching a larger resistance than a carbon steel column. Now, in a long column or a column with a high slenderness, the resistance is governed by global buckling, and in this case, the compressive stresses in the column will be below the limit of proportionality of stainless steel, and therefore the behavior will be predominantly elastic, and in this case, the stainless steel column will behave in a very similar way as a carbon steel column. So we're referring to this range of the stress strain curve. Now, for columns of intermediate slenderness, the resistance is also governed by global buckling, but in this case, the compressive stresses in the column will be between the limit of proportionality and the yield strength. And as you can see in this figure, this is the region where the detrimental effect of the nonlinearity is more pronounced. And therefore, in this range of slenderness, a stainless steel column can be expected to be less strong than a carbon steel column. Okay, so that was a brief introduction about how the stress strain characteristic of stainless steel affects its buckling performance. Now I'm going to give you a brief introduction about the Eurocodes. So when designing stainless steel structures in accordance with the Eurocodes, there are three main parts that need to be used. So we have Eurocode 0 that lay out the basic principles of design in the Eurocodes and tell you how to choose the load combination depending on the type of design you're doing. Then we have Eurocode 1, which gives the rules for calculating the design actions on the structure, and Eurocode 3, which gives the rules for calculating the resistance of the structure. So Eurocode 3 contains 6 main parts, and part 1 contains the general rules for the design of steel structures. And this is the part that you will need to use for most cases. Then you have parts 2 to 6, which provide rules that are only applicable to specific type of structures. Now, if you look into Eurocode 3 part 1, you will see that there are, at the moment, 12 different parts, although there are new parts that will be added in the future. So the rules for stainless steel structures are given in part 1.4, and this is a supplementary part that modifies the rules that are given in other part of Eurocode 3 part 1, which are the one you can see here. So Eurocode 3 part 1.4 covers the design of structures made of the three main alloy families. So that is ferritic, austenitic, and duplex stainless steel. And the type of section can be hot roll, welded sections, cold formed sections, and also bar sections. And as I mentioned previously, Eurocode 3 part 1.4 is a supplementary standard, which means that it only gives rules when the rules for carbon steel that are given in other Eurocode parts need to be modified in order to make them applicable to stainless steel. The standard covers the design of members and connections at ambient temperature and also under static loading. And for other design scenarios, such as fire design, design against fatigue, or other type of structures such as shell structures, the rules are given in other Eurocode parts together with the rules for carbon steel. Eurocode 3 Part 1.4 was first published in 2006, and since then it has been amended twice, and the first amendment was in 2015, and the second one was in 2020. Now, the modifications made during this amendment have been very localized, but currently all the Eurocodes are experiencing a major revision with the development of the second generation of the Eurocodes. So the intention of these revisions is to improve the ease of use, increase harmonization between the Eurocode parts, and to improve the design rules. And for Eurocode 3 Part 1.4, the second generation will provide more accurate and comprehensive rules for the design of stainless steel structures. So many of the parts for the second generation of Eurocodes have already been published to help engineers prepare and get familiar with the new Eurocodes. But until March 2028, you should still be using the first generation of the Eurocodes. Okay, so now I will talk about the design of stainless steel members in accordance with Eurocode 3 Part 1.4. So the design rules that are given in Eurocode 3 Part 1.4 follow the same approach as the one for carbon steel. So for tension members and restraint beams, the rules are identical as for carbon steel. In these cases, the resistance is not controlled by buckling, and therefore using the same rules that are given for carbon steel is conservative. Now, for the case in which the resistance is controlled by buckling, Eurocode 3 Part 1.4 applies some modifications to the carbon steel resistance equations, but try to keep the same format of the equations that are used for carbon steel. So the idea is that anyone that is familiar with the design of carbon steel members will have no issue designing stainless steel members. Eurocode 3 Part 1.4 also include rules on alloy selection, which Nancy briefly mentioned. And these rules are specific to stainless steel. And it also provides modification for the calculation of deflection to account for the gradual loss of stiffness of stainless steel. And Eurocode 3 Part 1.4 also include specific rules for stainless steel that permit to take advantage of the benefit of strength hardening. And I will describe these rules later on in this presentation. Okay, so let's talk about the design of for local buckling and the section classification limits. So the purpose of this classification is to assess the susceptibility of the cross-section to local buckling. Now, the risk of local buckling only exists when the member is subject to compressive stresses, which is why if the cross-section is subject to tension, you don't need to check its cross-section classification. So Eurocode 3 considers 4 different classes, which you can see represented in this slide. And these classes reflect the extent to which the resistance and rotational capacity of the cross-section is limited by local buckling. So according to Eurocode 3, the classification of the cross-section is given by the classification of the Moser-Lender element of the cross-section. And when you check the class of the cross-sectional element, you are basically comparing its width to thickness ratio against limiting values. And these limiting values depend on the yield strength of the steel, the stress distribution across the element, and whether the element is an internal or an outstand element. So an internal element would be the web of an I section, for example, which is supported on both sides by the flanges. And an outstand element would be the flanges, which are only supported on one side by the web. Here you can see the different equations that are used to calculate the cross-sectional resistance of columns and beams, depending on the classification of the cross-section. So cross-sections that are susceptible to local buckling are those that are classified as class 4. And for these cross-sections, the effect of local buckling is accounted for by using an effective area, or for the case of column, or an effective section modulus for the case of beams. And these effective properties are determined by considering that after local buckling takes place, only the part of the cross-section that are near to the corner regions are able to provide resistance. Now, if the cross-section is classified as class 1, class 2, or class 3, that means that local buckling is not considered to be an issue. So here I'm showing you some of the classification limits that are given in the Eurocodes for carbon steel and for stainless steel. So cross sections that are not able to satisfy the class 3 limits are classified as class 4. And as I mentioned previously, that means that they are susceptible to local buckling. Now, if you compare the class limits for carbon steel and stainless steel, you can see that the limits for stainless steel are more strict than the limits for carbon steel. And this is because of the more pronounced non-linearity of stainless steel. In this slide, you can see the equations that are given in Eurocode 3.14 for calculating the effective width of internal and outstand elements made of stainless steel. And in these equations, the effective width of the element is given as a function of the plate slenderness. And the definition of the plate slenderness is simply the square root of the yield strength divided by the critical elastic local buckling stress. So that's given here. And the Eurocodes give you the equation here for calculating this plate slenderness. Now here here there is an illustration of the effective width equations I showed you in the previous slide, and as you can see, the effective width curve for internal elements is lower than the one for carbon steel. And this is to account for the more pronounced non-linearity of stainless steel. Now, for outstand element, stainless steel uses the same effective width curve that is used for carbon steel. Okay, so let's talk about columns now. Here are the equations that are used in Eurocode 3.14 to calculate the resistance of stainless steel columns to global buckling. And these equations are the same as the one that are used for carbon steel columns. The reduction in resistance due to global buckling is taken into account by the reduction factor Xi. And this slide, in this slide, you can see the equations that are used to calculate this reduction factor. So as you can see, the reduction factor Xi depends on the non-dimensional slenderness of the column, which is given by the symbol lambda bar zero, lambda bar. The curve that expresses the reduction factor Xi as a function of the non-dimensional slenderness of the column is known as the buckling curve. So that would be this curve you see here. Now, the equations that are used to calculate the reduction factor Xi are the same as the equations that are used for carbon steel columns. but the imperfection factor alpha and the limiting slenderness lambda bar 0 are different. And in this figure, you can see how the imperfection factor alpha and the limiting slenderness lambda bar 0 affect the shape of the buckling curve. So the value of these factors take into account the nonlinearity of stainless steel, as well as the geometric imperfections and residual stresses that are present in the column. And because of this, they are different from the one that are used for carbon steel. And in fact, these factors are also different for different cross-section types and alloy families, because the residual stresses are different for these for different cross-section and also for different alloy families. So here I'm showing you a table that gives the values of the imperfection factors that are given in Eurocode 3 part 1.4 for different cross-section types and also different alloy families. For columns that are susceptible to torsional or flexural torsional buckling, Eurocode 3 part 1.4 says that you should use the same factor that is used for minor axis flexural buckling. And this figure shows all the different buckling curves that are specified for stainless steel columns in Eurocode 3 part 1.4. Okay, let's talk about lateral torsional buckling of beams now. So the design of beams against lateral torsional buckling is very simple to the design of columns, which I have just shown you. And here we have the equation that is used to calculate the resistance of stainless steel beams against lateral torsional buckling. And this equation is the same equation that is used for carbon steel beams. And in a similar way as for columns, the reduction in the cross-sectional resistance due to lateral torsional buckling is accounted through the reduction factor Xi sub LT. Here you have the equations that are used to calculate the reduction factor Xi sub LT. And the only difference between these equations and the ones that are used for carbon steel beams is the values that are used for the imperfection factor and the plateau length factor. So for stainless steel beams, the plateau length is taken as 0.4 for all type of cross sections, and the value of the imperfection factor is taken as 0.34 for cold form sections and hollow sections, and 0.76 for welded open sections and any other type of section. Now, you might have noticed that the equations for calculating the reduction factor Xi sub LT are the same as the one that are used for columns. But in this case, you have to use the non-dimensional slenderness of the beam, which is calculated based on the elastic lateral torsional buckling moment. Now, in the second generation of Eurocode 3 part 1.4, there will be some minor changes to this lateral torsional buckling curve. And there will be also a new equation for determining the reduction factor for lateral torsional buckling. Okay, so what about the calculation of the deflection of stainless steel beams? So because of the gradual loss of stiffness exhibited by stainless steel before the yield strength is reached, you should expect that a stainless steel beam will deflect slightly more than an equivalent beam that is made of carbon steel. Now, for simplicity, Eurocode 3 part 1.4 recommends calculating the deflection of stainless steel beams using the same traditional elastic equations that are used to calculate the deflection of carbon steel beams, but replacing the elastic modulus with a reduced elastic modulus, which is calculated using the equation that you can see in this slide here. Now, this reduced modulus is simply the average between the modulus E sub S1 and E sub S2, which are the second modulus calculated based on the stresses in the compression flange and the tension flange. Now, this slide shows the equation for calculating the second modulus. And this equation was derived from the Ramberg-Osgood material model, which is the material model that is used to represent the stress strain characteristic of stainless steel. And is able to account for this loss of stiffness of the material, as you can see here. So we have a simply supported beam subject to a uniformly distributed load. The maximum deflection, which takes place at midspan, can be calculated based on the reduced modulus of elasticity using the traditional elastic equation that is at the bottom of this slide, so here. And this method for calculating the deflection of stainless steel members gives adequate predictions when the stresses in the cross-section are below 65% of the yield stress. If your stresses are larger than that, the method becomes very conservative. Okay, so now I'm going to tell you about design rules that are going to be included in the second generation of Eurocode 3.14, and which has been derived for stainless steel specifically. And they are intended primarily to take advantage of the beneficial effect of strength hardening. So the rules I'm going to tell you about are the calculation of an average yield strength, which is used to account for the increase in strength that cold form stainless steel section experience during fabrication. And also I'm going to tell you about an alternative design method for calculating the resistance of stainless steel sections, which is called the continuous strength method. So I'm going to start with the rules for calculating an increased yield strength that result during the fabrication of a core form stainless steel section. And this increase in strength is because of the significant strength hardening of stainless steel. So when you plastically bend a sheet or a plate made of stainless steel, the material will show an increase in its yield strength due to the cold work that you apply. The graph you can see in this slide show why the strength of stainless steel increases as a result of cold work. So the red curve in the figure shows the yield strength of the sheet or plate material before it has been plastically deformed. And as the stainless steel sheet is bent to form the structural shape, the stainless steel material is deformed plastically, following the loading path and unloading path that is indicated in the red curve. So that would be this path. Now, after the sheet is bent, the stress strain characteristic of the cold form section will then be given by the blue curve. And this new stress strain curve will include an increase in the yield strength, some level of residual plastic strain, and also a reduction in ductility. Now, the reduction in ductility does not have a significant implication in design because the ductility of stainless steel is already more than enough. Now, the extent to which the strength increases is dependent on the amount of plastic deformation. And because of this, different parts of the cold form section will have different level of strength enhancement, depending on how much they are deformed. For example, the corners in a square hollow section or a channel section will show more significant increase in strength than the flat part of the section. So in this slide, I'm showing you how this increase in yield strength is distributed over a square hollow section and a circular hollow section. So for the square hollow section, the darker red around the corners represent a larger increase in yield strength, which result from the significant amount of plastic deformation that is applied to form the corners. Now, For square and rectangular hollow sections, the flat portions of the section might also show an increase in yield strength depending on the fabrication process. But this increase in yield strength will be less significant than the one in the corner regions. In a cold-formed round hollow section, you will also get an increase in yield strength, but this increase in strength is going to be uniformly distributed across the entire cross-section because the plastic deformations in a circular hollow sections are more uniform. So Eurocode 3.14 allows you to calculate an average yield strength for the entire cross-section based on the yield strength that is developed in the corner regions and also in the flat regions. Now, one important thing to take into account is that you cannot use the average yield strength when designing a cross-section that contains a weld or that is adjacent to a weld. And this is because of the annealing effect of the weld, which can completely remove the increase in strength due to cold work. So if the cross-section is near a weld, you will have to use the nominal yield strength when designing the cross-section. Now, the type of welds I am referring to are welds that are carried out after the fabrication of the section. So this would include, for example, the weld that you might use when attaching an end plate to the column, but if it doesn't include the seam weld that is used during the fabrication of the section, because the presence of this seam weld is already taken into account by the equations that are used to calculate the average yield strength. Eurocode 3.14 will also include the continuous strength method, which is a design method for calculating the resistance of stainless steel sections that take into account the beneficial effect of strength hardening. Now, one characteristic of the continuous strength method is that it does not require the classification of the cross-section into class 1, 2, 3, or 4, and treats all cross-sections in the same way. Now, one thing that is very important to take into account is that in order to use the continuous strength method, the section cannot be susceptible to global buckling. So you will need to make sure that you provide sufficient amount of restraint to your column or beams to prevent flexural buckling or lateral torsional buckling from happening. And also the continuous strength method is only applicable to the sections that you can see in this slide. So the way the continuous strength method works is first, you have to calculate the slenderness of the cross-section, which is given by the square root of the ratio between the yield strength and the elastic critical local buckling stress of the cross-section. Then you can use what we call the CSM base curves, which gives you the maximum compressive strain the cross-section can sustain before failing due to local buckling. And once you know the maximum strain the cross-section can sustain, you can use the CSM material model to convert the strains within the cross-section into stresses. And once you know the stresses within the cross-section, you can determine the resistance of the cross-section by integrating the stresses over the cross-section. Now, you don't need to do any derivation in order to use the CSM. Eurocode 3.14 will give you all the equations that you need to use to calculate the CSM resistance. So how much you can benefit from the CSM will depend on a few factors. So the more compact the cross-section is, the greater the resistance you will get due to strength hardening. Also, the shape of the cross-section and the alloy family will condition how much benefit you get from the continuous strength method. So, for example, austenitic stainless steels will benefit more than duplex stainless steels because of their superior strength hardening. So Using the CSM, you can get around, I would say, 20% increase in strength compared to the traditional design method that doesn't consider strength hardening. But if you are designing a cold form section, you could use the continuous strength method in combination with the average yield strength and get even better, greater benefits. Okay, so now we're going to move to the last part of this webinar, where I'm going to briefly mention the main points that you need to bear in mind when dealing with stainless steel bolted and welded connections. And then I will say a few words about fatigue. So one of the main things that need to be taken into account when designing stainless steel bolted connections is that the bolt, the nut, and the washer should have better corrosion resistance than the connected plates. And this means that you should use stainless steel bolts when connecting stainless steel members. And you should not use galvanized bolt, even in temporary structures, because of the risk of bimetallic corrosion. Now, many of the design rules that are used for carbon steel bolted connections are also applicable to stainless steel bolted connections. For example, the minimum and maximum spacing requirements for stainless steel bolts are the same as those for carbon steel bolts. So there's no difference there. And the equations given in Eurocode 3 part 1.4 for calculating the tensile and shear resistance of stainless steel bolts are also very similar to the equations that are used for carbon steel bolts. And if anything, they predict higher resistances. Now, one thing you should be aware of when dealing with stainless steel bolted connections is that they are more susceptible to galling than carbon steel bolted connections. So galling might occur during the tightening of the bolt due to the relative movement between the threads of the bolt and the nut and the high contact pressures that originate. So this could result in the breakdown of the protective oxide layer of stainless steel. And if this occurs, it could lead to the threads of the bolt and the thread of the nut to bond together, increasing friction. And in extreme cases, it could lead to the threads of the bolts and the nut to fuse together, making it impossible to continue tightening the bolt or even removing the bolt. Now, there are measures to minimize the risk of galling. And a very important measure is to select an adequate lubricant. So you should make sure that all the parts that are going to be in contact and in relative motion with each other are properly lubricated. There are other measures that you should take, and this includes reducing the tightening speed and also ensuring that the threads are free from grit or abrasive materials. With regard to the bearing resistance of stainless steel bolted connections, there are some differences with respect to the equations that are used for carbon steel. And this is because the equations that are used for stainless steel take into account the more nonlinear stress strain characteristic of stainless steel, and also the more significant amount of strength hardening. So the rules for calculating the bearing resistance of stainless steel bolted connections distinguish between plates with thicknesses of up to 4 millimeters and plates with thicknesses greater than 4 millimeters. And this distinction is made to align with the rules that are given for carbon steel bolted connections. Now, the bearing resistance equations for stainless steel also take into consideration whether the deformation at the bolt hole need to be limited or not. So for the case in which deformation is a design consideration, the equations that Eurocode 3 3.14 gives were derived by targeting a 1 millimeter deformation at the bolt hole under service loads. But if deformation is not a design consideration, Eurocode 3.14 allows the use of different bearing resistance equations that will predict greater resistances. Now, if you need to design a bolted connection that is used to connect stainless steel to carbon steel, the stainless steel part of the connection has to be isolated from the carbon steel part to prevent bimetallic corrosion. Now, bimetallic corrosion might occur when you have two dissimilar metals in contact with each other, and they are breached by an electrolyte solution. Excuse me. So when this is the case, the less noble metal, which in our case would be the carbon steel plate, excuse me, will corrode at a faster rate than if it was not in contact with the stainless steel plate. So the main strategy to prevent bimetallic corrosion is to separate the two dissimilar metals. And this is something that can be achieved by using the insulating washers and bushes. But because these insulating components are compressible, they can only be used in bearing type bolted connections. So the figure in this slide shows how you can achieve the separation between the carbon steel and the stainless steel plate using insulating components. And if you use this type of solution, you need to make sure that the bushing is able to resist the bearing pressure at the bolt. So in this case, it is recommended that you make sure that the threads of the bolt are not included in the shear plane in order to prevent puncturing the bushing. So this slide summarizes the main practical points to keep in mind for welded stainless steel connections. So first, austenitic stainless steels can generally be welded using any common welding process, and they are considered to be the most weldable family of stainless steels. Now, you still need to make sure that you follow good welding practice, and in particular, the welding procedure, the filler metal, the heat input, and the post-weld cleaning, they all need to be properly controlled to avoid cracking and to maintain corrosion resistance. Now, duplex stainless steels, on the other hand, need tighter control during welding, and in particular, the welding procedure needs to control both the minimum and the maximum heat input, because the welding thermal cycle can affect the phase balance of the material, which can affect the mechanical properties and the corrosion resistance of the welded zone. So you might need to carry out a post-weld treatment in order to restore the full corrosion performance of the welded zone. Now, one important practical issue you should bear in mind, and this has already been mentioned by Nancy, which is in particular for when welding austenitic stainless steel, is to do with distortion. So stainless steel, and especially austenitic stainless steel grades, are more prone to welded distortion than carbon steel because they combine a lower thermal conductivity with a higher thermal expansion, which means that the heat remains more localized while the material expands and contracts more. So this means that when welding stainless steel, it is important to control the welding sequence and also provide adequate restraint to avoid distortions. And this is why suitable welding procedures, qualified welders, and compatible consumables are so important. So the filler metal also should provide at least equivalent mechanical properties to the parent material, and it should also be capable of maintaining the required corrosion resistance. Finally, from a structural design point of view, the design rules that are used for carbon steel are generally also applicable to stainless steel welded connections, with just some minor modifications required in some particular cases. Now, a common question we often get, and in fact, we got it during the first part of this webinar as well, is whether stainless steel can be welded to carbon steel. And the answer to this is that it is possible, but you need to make sure you use the correct welding consumables. The welding consumables will have to be over alloy, because during welding, it will mix with the molten carbon steel, and therefore the final weld composition will be affected by dilution from the carbon steel side. And another important consideration is the risk of bimetallic corrosion at the junction between the carbon steel and the stainless steel. So in order to reduce that risk, any painting system that is applied to the carbon steel material should be extended across the weldment onto the stainless steel by about 75 millimeters. Okay, so here I go, my last slide for this webinar, which is about the fatigue resistance of stainless steel. And austenitic and duplex stainless steels are the alloy families that are most likely to be used for components that are subject to fatigue loading. And the fatigue design of construction details that are made of these alloy families is covered in Eurocode 3 Part 19. Now, similarly to carbon steel, the fatigue behavior of welded joints that are made of stainless steel is dominated by the joint geometry. There is a large amount of tests on austenitic and duplex stainless steel welded joints that show that the fatigue resistance of these alloy families is similar, if not slightly better, than the one for carbon steel welded joints. So because of this, Eurocode 3 Part 19 says that the fatigue resistance of construction details that are made of austenitic and duplex stainless steel can be calculated using the same fatigue curves that are used for carbon steel. Okay, so this concludes this webinar. Let me know if you have any question now.
So thank you, Dr. Francisco, for the excellent presentation. So let's first ask questions from the audience. 如果哪位这个专家有意见有这个问题的话，可以这个举手示意啊，就是示意，在这个如果是电脑旁边的话，有个屏幕的旁边有一个这个举手啊，举手。我看了线上呢，我看我们这个中国国内的这个不锈钢规范相关的几位这个主要编写者也在，然后我问一下啊，我看舒老师在不在？舒老师，你看你有什么这个想跟这个 Nancy 教授还有这个Francisco 交流的吗？我看你话筒已经解开了。好，可能舒老师这边看是不是解开？等一下啊，我看还有几位在。吴总，吴耀华，吴总，您的方便吗？有没有这个想这个跟这个两位专家交流的？ 好像不是很方便啊，不是方便但不要紧，因为这个我在这个叫我从这个屏幕上我看还有几个问题，有同学问的几个问题啊，稍等我一下。There are 3 questions. The first one maybe for Professor Nancy for the first half part. That's so I send this message to all the audience. Could you see the question? Oh, sorry. So you meant. Sorry. Let's with me for a minute.
Can you hear me okay?
Yeah. Yes. Excellent.
So the question concerns the fire resistance of stainless steel. And the good news is that we are going to be talking about that in some detail next Tuesday. The question says the metro entrance was exposed. How was the fire resistance included? Well, I didn't work on that project, so I'm not sure to what extent they took it into account, but the fire resistance of stainless steel is often critical for some of the applications. For example, when it is used on offshore platforms, and there is design guidance telling you how the strength and stiffness of stainless steel reduces with increasing temperature. And the design process is well understood, that takes into account both the thermal and the mechanical properties at elevated temperatures. So please come next week and you'll hear more about fire resistance.
好，非常感谢啊！这个下周的时候，下个星期二这个时间会对抗震和抗火都会有一些介绍啊，希望大家到时候再这个再参会啊。I think the second question is for Dr. Francisco. So could you
Yep. Can you hear me?
Yeah.
So the question is related to the average yield strength, and it says that for austenitic stainless steel cold form sections is taken as a fixed value, and the question is whether this fixed value can lead to an overestimation or an underestimation of the strengthening effects for certain materials. And I think the reason for the question is because of the different strength hardening, perhaps of different stainless steel alloys. So the average yield strength for austenitic, for any austenitic alloy, will be considered to be the same irrespective of the alloy. I believe that when deriving these provisions, different alloys were considered, and the rules are conservative, will be on the conservative side. Now, the rules do consider the difference between austenitic stainless steel and duplex stainless steel. So if you compare these two alloy families, you will see a more significant difference in the strength hardening. And these rules for calculating the average yield strength will take into account that difference. But if you are just looking at austenitic alloys, you will get the rules treat all the austenitic alloys in the same way. So, but the rules are obviously on the safe side.
Oh, I will translate part of them to the important part for the audience. 这个连续强度法呢，因为是第一次引入到欧洲规范，主要的工作可能还是在帝国理工大学的那个戛纳教授那边做的。现在呢，奥氏体的这条线啊，就是因为奥氏体的材料的这个品种也非常多。可能这种我刚才听这个 Francisco 博士说，这个里面啊，如果每一个给一条也是很麻烦的，所以呢，现在给了一个偏于安全的，给了一条奥氏体的线，然后当然还有一条双向钢的线，双向钢的线呢会比它稍微的强化会稍微弱一点啊，会稍微弱一点。OK， Let's see another question. The last question, I think. So could you see the question? I mean the question for the second half of our webinar. Defines determine. Oh, type of screw. Oh, that's a question about the screw connection. The tab. So maybe the next so the next week we show some design method for the self-tapping screw connection. Yeah.
Yes, perhaps we can include something. It's not a topic that we have covered because we are focusing on heavier load-bearing stainless steel members, but we'll certainly look at the question. I've made a note of it and see if there's something we can say about it.
Yeah. Okay. So next time we will give an answer for this question. So I actually have a question or comment for this the second part. In the second part, we show configuration to connect stainless steel plates and carbon plates. There's a figure. This figure. So if we use the high strength bolt and we have treated the surface using the machining method to treat the surface. So how it works after we applied the pretension load to the bolt?
Oh,
this is routine gasket works for this condition?
No, this solution you can see in the slide is only applicable to bearing type of connections. So these are connections that wouldn't have a pretension force. If you have a preloaded or a slip critical connection where you do need to apply a pretension force in the bolt, you wouldn't be able to use this compressible material. So in this case, you will have to rely on the coating you apply to the carbon steel plate. It is possible to achieve a connection. It's just that you have to separate the material just using the coating on the carbon steel plate.
Okay. Okay. Thank you. So any questions from the audience? So let me have a look. Okay, so thank you, Professor Nancy and Dr. Francisco, for this webinar. So next week, Tuesday, we will give the introduction to Chinese design code and the fire and the CMYSC design in the Eurocode. I think that, yeah. So 所以非常感谢这个 Nancy 教授和Francisco 博士给我们的一些这个非常细致的一些这个介绍啊。下周周二的晚上，我们会主要呢会对中国规范的新版的中国规范的一些规定进行一些介绍，也会涉及一些螺栓啊、焊接啊之类的问题。同时呢，欧洲规范的更加的详细的介绍，关于抗震抗火也会有一个详细的介绍，所以非常期待在线上再跟各位同学、各位老师，然后各位专家再相见啊。今天我们的这个就是线上的这个讲座就到这里，感谢大家啊，非常感谢，非常感谢。So see you next Tuesday.
Thank you, everyone.
Thank you. Bye-bye.
Goodbye.